In this video, we're going to give a short review of systems of linear equations. So a lot of what I'm going to be talking about in this video, you guys likely would have seen before when you've seen linear equations in middle school or high school, whenever the first time was when you saw these. Okay, so let me begin by just talking about what is linear algebra. What is this subject that we're going to be covering? So linear algebra is the field of math that emerges from solving systems of linear equations. So we're going to be reviewing systems of linear equations, the basics of them, and we're going to use that to build up a bunch of theory, and that's what constitutes linear algebra. Okay, so let's begin with an example. So let's find all x and y such that x minus y equals negative 2 and 3x minus 6y equals negative 15. So I want to find all values of x and y that satisfy both of these equations. So to do that, there are two methods that you guys likely would have seen before. So the first is we could solve for one variable in an equation. It doesn't really matter which equation we solve for a variable in, but we solve for one variable in an equation, and after doing that, we substitute. That's the key right there, and we substitute into the other. Okay, so this is something that you guys probably would have seen before, so I'm going to go through it kind of quickly. Okay, so for example, if I work with the first equation, x minus y equals negative 2, I could solve for one of these variables, either the x or the y. So if I solve for the x, for example, I get x equals, and moving the negative y over, I get y minus 2. So x equals y minus 2. And now let's take that and let's substitute that in to the other equation. So let me just write sub because we're substituting. So if I substitute that into my second equation, I'll get 3 times, and I know that x is now y minus 2. So I'm substituting that in. And then I still have the minus 6y equals negative 15. And then let's simplify. So if I distribute the 3, I get 3y minus 6. And then we have minus 6y equals negative 15. And then 3y minus 6y, that's negative 3y. And if I move the negative 6 over to the right, I get negative 9. And then dividing both sides by negative 3, I get y equals 3. So I know what one of the variables is now. I know what y is. And I could figure out x by plugging this value of y into either equation. So I could plug it into x minus y equals negative 2, or I could plug it into 3x minus 6y equals negative 15, whichever looks simpler. But I should get the same value plugging into either one. So I'm just going to plug it into x equals, I'm going to plug it into here, x equals y minus 2. If I do that, I get x equals 3 minus 2, which equals 1. And at this point, I have my answer. So I've figured out what x is and what y is. In fact, I could write my answer as an ordered pair, just to be concise. So x comma y is 1 comma 3. So there's just one solution to this system of equations. That's when x equals 1 and y equals 3. Okay, so this first method, I'm just going to call it substitution. So the issue with this method in general is that this method gets harder with more variables and equations. With more variables and equations. So the more variables I have, the harder it is to substitute. The more equations that I have, in this problem I just had 2 equations, but if we had more, the harder substitution gets. Okay, so what is the second method that we have for solving, a system of equations like this? Well, so you guys might remember it's to do stuff like adding equations together or subtracting them or multiplying an equation by a number and then adding it or subtracting it to the other one. So I'm just going to call all of those things like combined. Combine the equations to simplify them. to simplify them. So this method is sometimes referred to as elimination. You try to simplify your equations in a way that lets you eliminate some of the variables. Okay, so I've written the two equations that we have here, and what I'm going to do is I'm going to start to combine these. So here's how I'm going to combine them. I notice that I can get rid of this 3 if I multiply the first equation by -3, and then I add it to the second equation. So I'm going to make a note that I'm doing that. So I'm going to say I'm doing -3 times the first equation. So for the first equation, I'm just going to call it R1. R1, I'm going to say, is this first row, x minus y equals -2. R2 is this second row, it's the second equation. So I'm multiplying the first equation by -3. I'm going to add it to the second row, to the second equation, to cancel the 3 out. And then I'm going to replace that with the second equation. Okay, so that's just a little bit of notation to help me stay organized. Okay, so I'll still have the first equation, x minus y equals -2. But if I multiply the first equation by -3, and I add it to the second equation, what I'll get is I'll actually get 0x. So if I multiply this -y by -3, I'll get positive 3y, and positive 3y added to -6y, well, that's -3y. And then if I multiply the -2 by -3, I get positive 6, and positive 6 added to -15, well, that's -9. Okay, so I've eliminated the variable x in this second equation because 0x is just 0. Okay, so at this point in my second equation, if I divide both sides by -3, I get y equals 3. So I got y. And then by doing the same thing I did in the first method, at this point I could figure out what x is by plugging in y into either of these equations. And if I do that, I get x equals 1. Okay, and that's the same answer that we had in the first method. So x comma y equals 1 comma 3. Okay, so it's good that we're getting the same answer in both of these ways. Alrighty, so let's give a geometric picture of what this looks like. So let's give a geometric picture. Okay, so I'm going to draw my axes. I'm going to draw my x-axis and my y-axis. And then I'm going to draw what the graph of each of these equations look like. So both of them are lines. Okay, so I can draw them. So x minus y equals -2. And it turns out that that looks something like this. It turns out it has positive slope if I just rearrange it a little bit. And it turns out that the y-intercept of it is +2. Again, I have to rearrange it a little bit to get that. But that is the line x minus y equals -2. 3x minus 6y equals -15. That's also a line. Except it turns out it looks something like this. The slope is a little bit flatter. And again, to see that, I would have to isolate the y. I would have to get the y by itself in this equation. Okay, but that's not hard to do. So I'm just going to go ahead and draw the line for you guys. So this one in green. So this is the equation 3x minus 6y equals -15. So graphically, where these two lines meet, that is the point that we've just found. So that is the point 1, 3. All right. So in general, when we have a system of two linear equations like this that I can draw in the plane, there's 3 possibilities for what the lines can look like. The first is, like in this picture, the lines intersect. The lines intersect exactly once. So the lines will sometimes intersect exactly once. And if that happens, then there is one solution to the system of linear equations, just like we found here. It was just the point 1, 3, one solution. But that's not the only possibility. The lines, so the second possibility is the lines might not intersect. The lines don't intersect. So that could definitely happen. And if they don't intersect, well, then there's no solution. So let me just draw a quick picture of that. So if I had, my axes, and then maybe I have one line like this. What would it look like if I have a second line that doesn't intersect this first one? Well, those two lines would have to be parallel and kind of spaced out from each other, so they're not allowed to be the same line. So that's what the second situation looks like. But there's one more possibility, which is the lines might be the same. The lines are the same. So let's draw a picture of that. So let me draw that one on the left here. So if the lines are the same, let me scooch this down a little bit. If the lines are the same, what would happen is, I might draw my first line. Let me put that one in blue. And then I draw the second line, and the second line is the same as the first one. If I draw it in red, I get the exact same line. But in this situation, how many intersection points are there? Well, there's infinitely many. Every single point on this line is an intersection point. So there would be infinitely many solutions. There are infinitely many solutions in this third case. All right. So let's look at one more example in this video. So this is example 2. So I'm going to up the difficulty a little bit this time. This time there's 3 variables. I want to find all x, y, and z such that x minus 2y plus 4z equals 1 and x plus y plus 7z equals 3. Okay, so I want to find all values of x, y, and z that satisfy these 2 equations. In other words, I want to find the intersection of the graphs of whatever these 2 things are. And if you guys have seen this before, maybe either in high school or perhaps if you guys have taken multivariable calculus, these are planes. If you haven't seen that before, no worries about that. That's not a big deal. We'll talk more about them later. Okay, but how do we solve something like this? How do we solve a system like this? Let's talk about the solution. So I'm going to begin by just writing down my 2 equations. So x minus 2y plus 4z equals 1. So that was one of our equations. The other one was x plus y plus 7z equals 3. Okay, so I'm going to try our second method. I'm going to try to combine these equations in a way that lets me eliminate some of the variables. So how can I do that? Okay, so I notice that both of these equations just have an x at the front. So if I subtract them from each other, the x should cancel. So maybe let me do the second equation, I'll call it R2, minus the first equation, R1. And I'm going to do that and then write that where the second equation is currently written. So that's what this notation means. Okay, so the first equation, I'll just keep it exactly how it is. X minus 2y plus 4z equals 1. And now for the second equation, I'm going to replace it by doing the second equation minus the top one. So if I do that, I'll get x minus x, which is 0. Okay, and then if I subtract the y terms, I'll get y minus negative 2y, which is 3y. And then doing 7z minus 4z, I'll get positive 3z. So that's what I get on the left-hand side. On the right-hand side, 3 minus 1 is 2. All right, so now I have this new equation, 3y plus 3z equals 2 that I can work with. And that equation looks the simplest out of the ones that I have so far. So I'm going to focus in on that equation. So I got 3y plus 3z equals 2. So now let me try to isolate one of the variables here, solve for one of the variables. Okay, so it doesn't really matter which one I do, but let's say I isolate the y. So if I do that, I would get y equals, by moving the 3z over and dividing by 3, I would get y equals negative z, and I would get plus 2/3. So negative z and plus 2/3. Okay, so I don't know what y is as a number, like y is still in terms of a variable, but I can't really see a way to, eliminate the z here. I don't have more information. So let's take this, let's take what y equals, and let's substitute this back into our other equation. So our other equation was x minus 2y plus 4z equals 1, and let's substitute into this. So if I do that, I'll get x minus 2 times, so y I'm going to substitute in for. That'll give me negative z plus 2/3. That's what y equaled. And then I still got this plus 4z, and then this whole thing equals 1. All right, so if I simplify this part right here, if I distribute the negative 2 in, I'll get positive 2z, we'll get minus 4/3, and then we still have that plus 4z at the end. Okay, so let's use that to isolate the x now. So if I isolate the x, I will get x equals, so I know 2z plus 4z, that's 6z, and moving that to the right-hand side, I'll get minus 6z. And then I have this minus 4/3, and with the minus 4/3, if I move that to the right-hand side, I'll get 1 plus 4/3. And getting a common denominator, that is 7/3. Okay, so we know what x is at this point. X equals negative 6z plus 7/3. We know what y is up here. Y equals negative z plus 2/3. Okay, so at this point, we're actually ready to write down the general solution. We are ready to write down the general solution. So the general solution, so in this problem, we have not just an ordered pair, we have an ordered triple, 3 variables. Okay, so x always looks like negative 6z plus 7/3. Y looks like negative z plus 2/3. And z can be anything. So the z, I'm just going to keep it as it is. Okay, so when we write this, we say that z is what's called a free variable. So z is a free variable. So by plugging in different values in for z, I'll get all the possible solutions. So because z can be anything, any real number, there are an infinite number of solutions here. So our general solution of this problem look like this. So for example, if z equals 0, which is one possibility, if z equals 0, then we get the point 7/3, comma, 2/3, comma 0, and that's one of the solutions. We can get all the other solutions by letting z be other values. Okay, so what is this like? What does this look like geometrically? So this is what I'm going to end with. I want to draw a geometric picture of what this looks like. So geometric picture. So I mentioned that when we have a linear equation, like we did here, but with 3 variables, that corresponds graphically to a plane in 3D space. So let's imagine we have one plane corresponding to one of our equations, and then we have another plane corresponding to our other equation. And what we're doing here is we're finding where these planes intersect. So let me just try to draw this. So I'll have another plane, let's say it looks something like this, and then part of the plane will go like above the other one. And then let's say like here it's starting to intersect. Let's say here also it's starting to intersect. And then I'm going to draw the bottom part of this plane. So the bottom part will kind of go down. And then at this point it's going to go underneath the black plane. So I'm going to draw like a dashed line to indicate, oh, it's going underneath. And now let's draw a dashed line to indicate, oh, that's the other part that sort of went underneath. And what does the intersection look like? Well, the intersection would be something like this green line that I'm drawing right here. That's the intersection line. That would be my intersection line. So in this particular picture, we have 2 planes that intersect in a line. So it makes sense that when we wrote down our general solution, that there were an infinite number of triples like this, an infinite number of points, because there are an infinite number of points on this intersection line. So 2 planes don't always intersect in a line. Like it's possible for 2 planes to be parallel, and have no solution, or for 2 planes to be the same, and also have an infinite number of solutions. But in this particular example, they did intersect in a line. Okay, so the final thing I want to write here is, what I'd like to be able to have now is, we want a systematic way. We want a systematic way to solve complex systems of linear equations. Because I just upped the difficulty a little bit from example 1 to example 2. I just increased the number of variables by 1. But sometimes, there may be way more equations than just 2. Sometimes there will be a lot more variables than 3. And the systematic way that we're going to use to tackle a system of linear equations is to use matrices. So we'll talk about that in the next video.